Today we're going to continue with our science panel, moving away from the clinical stuff and talking about the epidemiology study. So we'll hear more from Dr. Maldonado today and Dr. Ryan today. To kick us off this morning, Commissioner Toby Baker is going to come and give us a few words.
Thank you for being here this morning. I appreciate it. My goal is to try to not put you to sleep in the first 10 minutes of the day, but so I'll attempt to do that. But my name is Toby Baker. I'm a commissioner. Kudos to Dr. Honeycutt for putting this together. And welcome to Austin, Gig'em Aggies. Sorry. Anyway, it's important that you're here, and I'm kind of scribbled down a few notes this morning about the way I feel about public policy as it relates to environmental policy. One, I think this policy area has to be built on science and data. It has to be done within the confines of the law, and then finally, you have to sprinkle a little common sense over the top of it to get it right. I've been concerned. I've been doing this now. I've been in this world for over 10 years, and I'm concerned about what I see in this area of public policy because I feel like there's two things in particular that are moving us away from that three-leg stool that I talked about. The first is, the courts are not arbiters of science, and there's no real meaningful way outside of the comment process to get your science considered. And what that means is an agency like TCEQ, who has a wealth of knowledge, scientists, attorneys, engineers, the data that we have maybe gets a glance, but there's nothing that I can point at that says that it did get a thorough review. The second thing that concerns me is the politicization of the science in regards to this policy. And that's not on just one side of the aisle. I think that's on both sides of the aisle. And what concerns me about that is it's making it very hard to have an actual real conversation about what the public policy should be because nobody can agree on what the science is. And so it's creating this rift that it's going to be tough to bridge. And I think things like this are our opportunities to be able to bridge that gap. So I really do appreciate you being here today. So why does it matter about whether we get this right? And the reason why it matters is because there are real costs associated with this. You may have heard about, you've probably heard, if we get this wrong, it's going to cost us billions of dollars. I'll bring it to the local level here in Austin. The irony of ironies is that it'll make it harder to build roads in a town that is gridlocked for several hours every single day, which actually increases the amount of ozone in the air. But it'll make it actually harder to build roads. But I go even further than that, make it more personal than that. I grew up in Beaumont, came from a middle-class family. Remember my parents talking about the cost of putting fuel in the tank of their car, the cost of putting food on the table, the cost of turning on the lights. And there's been a lot of talk over the last 10 years about the middle class and how the middle class relates to tax policy. And I think what gets lost a lot of the time is how the middle class is impacted by regulatory policy. Because every time we do something like this and we get it wrong, or when we get it right, oftentimes the necessities become just a little bit more expensive. And so what does that mean for a middle class family? I think it meant for me going to school and graduating with a mountain of debt. Whereas I think my parents worked hard to try to get to a place to where that wouldn't happen, but that was the reality. And I think the reality that a lot of our students face now coming from families like that. The second part is, in even drilling down even further, the ability to afford health insurance. When you make necessities more expensive, those things on the margins start to fall away, and it has a real impact on people around this state and around this country. And the interesting thing about this policy, it's not about just the state of Texas, it's about the entire United States. And so I really appreciate you being here today. I'm really looking forward to the outcome of what is produced, and I guess the findings and the recommendations, and looking forward to sort of setting the politics aside and being able to focus on just the science for a few days. And so I really do appreciate what Dr. Honeycutt's done. I appreciate the time that you guys have put towards coming down here, and I really appreciate you coming and being part of this process as well. So with that, I'm not going to keep you any longer. Thank you for being here today, and I look forward to your findings. Thank you.
Okay, well, welcome back. What I'd like to do is just very briefly comment on yesterday and share with you what some of the findings were. I'm not going to try to summarize yesterday. We had really wide-ranging discussions. One thing that did come clear to me as we were talking, however, is that we have really not a three-dimensional problem. We have a four-dimensional problem. We have the idea of concentration, and we have ventilation rate, and we have the amount of time. That's the three dimensions that Dr. Lang talked about. And we also have this idea of upregulation, because the data seems to show that if you're exposed over longer times, your body regenerates or replenishes protective enzymes, and somehow that has to work into the process. I'm not sure how that would work, but that was just one idea that came up. What we're going to be doing is we'll be writing notes up of yesterday's session, and we have several note takers that are doing that, one from our group, one from TCEQ, and then those will be shared with the authors and the panel, and the authors and the panel will get the chance to annotate their respective sections, so that if there's changes in the panel discussions, the panel gets to change it, and vice versa. You don't get to necessarily cross over and change somebody else's stuff. And that will be done probably within several weeks afterwards, and so that draft will be out and about. So at this point, we get to switch engines or gears, or however you want to say it, and go into epidemiology studies. And today we're going to have Dr. Julie Goodman make a presentation. Dr. Goodman is blessed that she's both a toxicologist and an epidemiologist, so she can bridge the gap, which is good for toxicology folks like me. I always look to people like that. And Dr. Maldonado. We're going to get this at the end, George.
You know, George, he's been practicing.
Yeah, I've been practicing too.
Just call me George.
Yeah, George. Okay, so in any event, we're blessed with people with that expertise, and without any further ado, we're going to go to Dr. Goodman for the presentation.
Thanks, Mike. And before I begin, I just want to mention I've been working on NACS issues for almost 10 years. I've worked with the American Petroleum Institute, the American Forest and Paper Association, and several other industry trade groups. And for the last 2 years, I've been doing other work on these issues with TCEQ. So for a brief overview of the ozone epidemiology, I have here EPA's causal determinations. And we're going to talk a lot about EPA's criteria for determining an association as causal, likely causal, suggestive later this morning. But for right now, EPA looked at many health effects. The three on which it focuses most are respiratory effects, including mortality, all-cause mortality, and cardiovascular effects, including mortality. And EPA looks at short-term exposure and long-term exposure separately. EPA defines short-term exposure as 30 days or fewer, and long-term exposure is greater than 30 days. And as you can see, in the 2008 review, EPA concluded that respiratory effects were caused by ozone, and this causal determination remains the same in the current review. But all-cause mortality and cardiovascular effects, EPA concluded evidence was suggestive in 2008, but now conclude that it's a likely to be causal association. And for long-term exposure, all of the causality determinations have gone up from suggestive to respiratory effects to likely, from little evidence or no conclusion for all-cause mortality and cardiovascular effects to suggestive for both. And just to be clear, suggestive EPA defines as having one high-quality study showing an effect. So there could be hundreds of high-quality studies showing no effects, but as long as there's one high-quality study, EPA concludes that it's a suggestive association. And briefly here, I have the administrator's proposed conclusions on short-term and long-term health effects. And so what she said for short-term is that there's evidence for small reversible changes in lung function and inflammation, respiratory emergency department visits, hospital admissions, and all-cause mortality. And then for long-term, that there's evidence for respiratory morbidity and mortality is likely to be causal. But what's interesting is if you look elsewhere in the proposed rule, Sonia Sachs is going to be talking about the risk assessment over lunch. And EPA conducted 2 risk assessments, one based on the controlled exposure studies and one based on the epidemiology studies. And the administrator said that she places relatively less weight on the epidemiology-based risk estimates. And the 3 primary reasons are the heterogeneity across locations, so the heterogeneity in risk estimates, the issue of exposure measurement error, or that we can't really be sure what exposures are in these studies. We'll be talking a lot about that this morning, I'm sure. And also the shape of the concentration response functions at lower portions of ambient distributions are highly uncertain. So it's unclear, I mean, how these issues can only impact the risk assessment but don't impact the causal determination. It seems that they don't play as much of a role in the EPA's conclusions regarding whether ozone causes these effects, only whether you can do a risk assessment based on these effects. And then in terms of long-term exposure, she acknowledged that there was only one well-designed long-term mortality study by Jarrett et al., but did acknowledge that there's uncertainty about the threshold. So EPA assumed there was no threshold when they did their modeling, but if you actually look at the data, and we can look at that today if we want, it looks like it actually does support one, and that should be considered. And then there's many uncertainties with the epidemiology data, and we'll get into that today. But just briefly, to bring everyone up to speed, there's several different kinds of epidemiology study designs, and I'll talk about the primary types over the next few minutes. There's different types for looking at the short-term exposure for hours, days, or weeks, and the long-term exposure for months or years, or then cross-sectional studies looking at a point in time. So first we have time series studies. And in these studies, we're looking at aggregate estimates of exposure and health. So we have these giant databases looking at hospital admissions or death records or emergency department visits. So we can calculate numbers over cities or regions, and then we can get air pollution data from central air monitors and look to see if there's any correlations. And then case crossover studies are a kind of time series studies, but in this case, each person serves as his or her own control. So the idea is you have periods of time that are considered the kind of the case period, so the time when an event occurs, be it a hospital admission or an asthma attack, and then you pick another point in time where the event hasn't occurred, and then you compare ozone concentrations to see if there's a difference. Next, we have panel studies. And in these studies, you repeatedly assess the health status of individuals over time, sometimes hundreds of times. And exposure can be either measured personally, people carrying around packs to measure exposures, or using the central site monitors again. And these studies are often used to investigate lung function and asthma symptoms. So those are all for the short-term exposures. For long-term exposures, longitudinal cohort studies are the most common types of studies. In these studies, you have a group of people, and this is sort of an oversimplified version, where you can categorize them into exposed and non-exposed, and then see who gets disease and who doesn't, or who has an event and doesn't, and see if there's any difference. In the ozone studies, rather than just 2 categories, you actually correlate it with the specific levels of exposure. And then finally, cross-sectional studies. It's a snapshot, hence the Polaroid. The idea is that exposure status and disease status are measured at one point in time or over a short period. There's no follow-up. And the idea is you're looking at disease prevalence among exposed and non-exposed. And this is, one of the issues with this is because you're just looking at a point in time, anybody that was cured or anybody that died from the disease is going to not be counted, and so it might not be an accurate assessment of whether exposure is causing disease. And also because it's the same time, obviously the exposure has to come before the disease, so you don't necessarily know what the exposure was beforehand. So this is just a very brief list of some of the strengths of epidemiology studies and why they can be good for assessing causal associations. First, you can assess health status over a large population, literally millions of people. We have these huge databases that we can take advantage of. You can also look at ozone levels changing over time because we have these air monitors. And in certain studies, we actually can look at individuals. We do have individual data and can make inferences about what's happening in individual people. You can also control for temporal trends. For instance, you can get data on temperature or meteorology, pollen, things like that, and you can incorporate those in the analysis. And you can also look at other sort of time invariant characteristics, such as things like often smoking status and socioeconomic status can change, but often they remain relatively consistent over study periods. But epidemiology studies are not without weaknesses. And part of this is that these are observational studies. You're looking at what's happening in the real world. It's not an experimental study where you put someone in a chamber and say, here's the exposure you're getting. Or you have rats that are all genetically identical and giving them, treating them all the same. People are living their lives. They have many exposures. They're inside, they're outside. So there's all these kind of issues you have to deal with. So some of the main ones, and the ones that I hope we spend time talking about today, are this idea of ecological fallacy. This is a technical term. So we call these ecological studies where you have exposures in aggregate and health status in aggregate. You don't have, for any person, their particular exposure and their particular health status. So you don't know if a person had an asthma attack or if a person died, what their specific exposure was. So it might not be the exposure that caused that effect. Confounding is a huge issue. If you find an association between ozone and a health effect, is it really ozone or is it some other factor that's correlated with both ozone and the health effect? Like pollen, upper respiratory infections is something that people are looking at. Other pollutants like particulate matter. I mentioned with the cross-sectional studies prevalence measures. So instead of looking at the incidence of disease, you're looking at a cross-section of who has the disease. So you're missing people that either died that had the most severe diseases or people that were cured. There are a lot of issues in certain epidemiology studies with compliance. So in these panel studies, where people are required to, test their lung function very often, or people are supposed to write down in a diary things that happened in their day. A lot of these studies have low compliance. It's a lot of work, and over time people drop out. Exposure measurement error is a huge issue. We have most of these studies use these central air monitors. Here's a picture of one. Is this in Texas? Yeah, it's from courtesy of Mike Honeycutt. And people don't spend their day standing by an air monitor. They spend most of their time inside. There's very little correlation between ozone exposures inside and outside. They're at home, they're at work, they're moving around. And so that's one of the biggest issues in these air pollution studies. We also have disease measurement error. For example, it's very difficult to diagnose asthma in an infant. So how do you, or a toddler, so you might be misdiagnosing and that could impact results. Model misspecification. This is when the statistical model you use isn't appropriate. I think maybe an easy example is if you look at temperature, extremely low temperatures and extremely high temperatures can impact health. So you have kind of a U-shaped curve, but if a study, instead of assuming a U-shaped curve, assumes a linear curve, you're misspecifying temperature, and that could, by not appropriately characterizing temperature, that might impact the association you measure between ozone and a health effect. Then there's model selection bias, and this occurs when you have a whole bunch of statistical models you can choose from, and you choose the one that makes your results look a certain way. Often the most, the models that show the most significant risks are often the ones that are shown or focused on. whether or not they're actually the most appropriate for the data at hand. And in a similar way, we have this idea of the multiple comparison issue, where these studies look at hundreds or thousands of different associations and really focus on the ones with statistical significance and not really paying attention to the ones that show no association at all and what they mean together. And finally, we have publication bias, where studies that show effects are more likely to be published than other studies. And then the final concept I wanted to bring up is heterogeneity, which isn't really a limitation, it's just a fact of life, I guess, where the idea is, this is a study by Smith. Each row is a city, and what we're looking at is the percent rise in mortality per 10 part per billion rise in 8-hour ozone. And the vertical line down the middle is zero, so no impact on mortality. The circles to the right are showing an increase in mortality, the circles to the left a decrease, with the lines representing the confidence intervals. And what you can see is that in some cities, ozone's associated with fewer deaths, and in some cities with more deaths. And so what does this mean? How do we interpret this? So that's another issue we have to deal with epidemiology. So I think that sums up kind of the types of studies that are done and some of the main issues, so we can start talking about how do we interpret these studies in light of all these issues.
Okay, Dr. Goodman, thank you very much. So we're going to run this a little bit differently than yesterday. We're going to let our science panel ask clarifying questions first, and then we're going to go to our policy panel, and then we're going to open it up to the audience. So if you have clarifying questions from the audience, we'll do that instead of writing the notes out. So to our science panel, any clarifying questions?
The
Yes.
thing that concerns me a lot here is the heterogeneity. And what are the implications for causality by seeing a large amount of heterogeneity?
So can we pull up that last slide and maybe talk right to that? Okay, go ahead, Dr. Goodman.
I'm happy to answer. I'm sure George has plenty to say on this too.
Yep.
No, I think it's a huge issue, because obviously ozone is not protective in some cities and causing mortality in others. I think it's a sign that there's some other factor associated with ozone, and that's why you're seeing these different associations.
Would the term be that it's a surrogate for something else? I don't know what the proper epidemiological term is. So when, would ozone be a surrogate for another cause? Is that the proper term?
It could be that, or it could be more complicated than that.
Oh, okay.
I mean,
So Dr. Maldonado, do you want to answer?
Yes, I do. I'd like to comment on that. When you're looking at heterogeneity, when you're comparing the results of different studies, you want to be careful that you're comparing studies that all ask the same question. If different studies are asking different questions, then there may be reason to believe that the true causal effect is actually different for those different, true causal answer is different for those different questions. And so when I see a graph like this, and Julie and I have talked about this, what I would have preferred was more information about exactly what kinds of questions each of those studies are comparing. For example, are they all comparing or contrasting the same exposure levels? Or
Wait, let me just interrupt. This is actually one study looking at different cities. So it is all asking the same thing.
Well, actually asking, I would wonder if it was asking the same question in each of the cities. So is it the same exposure comparison in all of the cities?
Yes, it's a increase in mortality per 10 part per billion rise in 8-hour ozone.
Okay. Well, if that's all fine, the next thing you want to look at is the idea of the true causal effect can be different for different groups of people depending on their characteristics. And so obviously, not obviously, I think the characteristics of the people in these studies are probably different in these cities. And so that's an important component of a causal question. A causal question, a specific causal question is comprised of the exposure contrast, or the exposure levels that are being compared, the characteristics of the population that you're studying, and also the time period for the exposure timing, and also the timing for the observation of the outcome. And so for this, or any consideration of heterogeneity, I would first want to ask myself, am I really asking the same question of these different groups? Clearly, these have the potential to be different target populations, to have different characteristics, which may explain the difference between the studies.
Okay?
Right.
And there's more to heterogeneity than just heterogeneity, though.
Right. Well, and I think kind of adding to that, I think what you're saying too is that, so it's possible, maybe it is causal in certain cities and not others because there's characteristics of people in those cities or
Yeah.
other factors in those cities. But I think a very important thing is, because of that, it's not appropriate to just take a weighted average of all these cities because of this heterogeneity and just say, okay, well, you take them all together, sum them up, and then this is what the risk is in America.
Dr. Phelan, did that answer your clarifying question?
Yes, it does. I had a second question.
Sure, go ahead.
Okay. You mentioned a rise of 10 parts per million, or 10 parts per billion, or something like that. And we see this measure, and as opposed to at a concentration level. I've seen that being used deceptively, where rise means that you take a running average, and if you have several relatively clean days, and then you go to an average day, that'll be called a rise. And there's sometimes a confusion. Well, I heard a pulmonologist say, well, it was the 3 clean days that caused the problem. So have you seen in the literature any sort of confusion between a rise, just meaning the slope of dose response curve, versus a rise meaning what today is compared to what the previous 4 or 5 days were?
That's a big question.
Yeah.
I think it's,
Yeah, it's sometimes obscure in the literature.
I mean, there's I think a lot of different concepts brought up in that question. One has to do with the averaging time, and Sabina talked about that a lot yesterday in kind of relating the controlled exposure studies. So this is the 8-hour ozone. So what it is in a 24-hour day, there's 24 kind of 8-hour windows, and you take the average in each window, and then the maximum of all of those 24 measurements. That's what you're talking about, and you're looking at that association.
Okay.
But you could do the 1-hour max, you could do the 12-hour, and you can get different answers depending on how you look at it, and there's that part of it. The other part has to do with, many of these studies assume no threshold. So there's a risk down to 1 molecule, down to 0 molecules of ozone. And so you're starting with that assumption. If you're starting with that assumption, you're going to get an answer that supports it. I mean, I don't know how you evaluate dose response if you're assuming there's responses at these low exposure levels, because that might not be appropriate.
Okay?
Oh, and lags, sorry, there's just one more thing, and that has to do with lag time. The other thing that studies do is they look at different lags. So they say, you're exposed today, what was your health effect 1 day from exposure versus 2 days versus 3 days, or within 1 day, within 2 days. So many studies look at different lag times to see if there's an impact. And this gets to one of those issues of multiple comparisons. So if there's a biologically plausible lag and you see associations and you see consistently with the same lag, that suggests there might be something there. But if you see things with strange lags, like exposure to ozone has no impact over 3 days, but on the 4th day, there's an association with mortality, that might make you question whether or not it's really ozone or something else.
Again, Dr. Phelan, that answers your question. Okay, other clarifying questions, Dr.
Can
Patel?
I follow up with that?
Yes.
One thing to be really careful of when we're talking about observed effects, whether they appear to be causal or whether there's heterogeneity, remember that, as Dr. Goodman pointed out, there are limitations in epidemiologic studies. And unfortunately, we're still at a point in time where most of the things that go wrong in a study are not adjusted for. Did I just lose my microphone?
Yeah.
Okay. Should I, oh, there it is.
There you
Okay. So ideally, what we would like to have in front of us when we're talking about, the magnitude of effect, whether it's causal or not, or is there heterogeneity and what does it mean? Ideally, what I would like to have is results from a study with no measurement error, no confounding.
That'd be great.
That would be amazing.
Are you laughing? In other words, without the noise or the uncertainty which is not quantified in most epidemiologic studies. So we do try to control for confounding, but confounding is actually a lot more difficult to deal with than most people realize, so I don't think we do a terrific job at that. Typically, exposure measurement error, which is often called the 800-pound gorilla of epidemiologic bias. The question is, how much bias can exposure measurement error cause? Pretty much as much as it likes, as much as it wants. Typically not corrected in epidemiologic studies, rarely, very, very rarely, and I'm sure exposure measurement error is not corrected in these studies that we're talking about right here, right, Julie? Disease measurement error is also not corrected for in studies. I wish it was, and all of these limitations that Julie talked about, for the most part, the only thing we deal with, we try to deal with is confounding, and as I said, we don't do that very well. So it's hard to talk about whether an effect is real or not, whether it differs across different target populations, when you're looking at epidemiologic results that have assumed that whatever went wrong in the study is not important.
Okay.
And I'm actually kind of surprised and disappointed that we're still at this point, because this was one of the major concerns of mine when I was a graduate student 30 years ago, and I thought surely by now it would be standard practice to correct for all these things that we know are important, like exposure measurement error. And given that we often don't know how much measurement error, how much of each of these problems we have, it would generate some uncertainty. And I was hoping that by now that we would be doing some kind of uncertainty analysis or probabilistic sensitivity analysis to quantify how much uncertainty we have in these study results. If I had that, then I could sit down and we could talk about, is it causal or not, given the uncertainties that I've quantified because of the study problems, is there heterogeneity, so on and so forth. So I'm a little disappointed that we are not yet there, and I hope that in 50 years that we will look back at the things that we do now, the things that we ignore now, and just shake our heads and say, what were they thinking?
Okay, Dr. Maldonado, thank you very much. Dr. Utel, you had a question?
I do, just one comment. I mean, it's been a pretty powerful study by Richard Smith. We're looking at one of the strengths is that there isn't an argument about disease measurement error. I mean, mortality is pretty much diagnosed the same way by everybody. But when you get to morbidity, Dr. Goodman, do you see these same kinds of studies on heterogeneity, or are they not done? Because there you have, in fact, a variable that's even more problematic in the way the diagnosis is made. And so I'm not sure if this is the one case where there's heterogeneity that's been shown, or in fact, when you look at morbidity, you see the same kind of finding.
Yeah, did you want to address that?
Yeah, I don't think there are, to my knowledge, studies like this on morbidity endpoints. At least in the risk assessment, they're really just like single city studies that are used. I can't think, I mean, these mortality studies are really the ones where they look at, the multi-city.
There are,
Do you, yeah,
so there are a couple that have looked at, I think the endpoint is asthma exacerbations. Oh, sorry. I think the endpoint is asthma exacerbations. There are a couple of multi-city studies. Schildkraut and O'Connor. I think there are a couple that look at, they're not this big, they're looking at maybe 8 cities.
Yeah.
And they do, and at least one of them shows individual city results, and they do show that heterogeneity. So in some cases, just one city will show, of the 8, will show an association. I think maybe Mortimer also has done a couple of, maybe 8 cities, and has shown heterogeneity with it.
Yeah.
So these would be useful to have as part of our set of studies to look at, Dr.
Well-
Utel?
Well, I think
They're-
if you want to
They're not.
talk about heterogeneity,
Highlighted
again,
too
you
much.
want to have more than one study. I mean,
Right.
I understand that there are multiple studies involved here, but whether heterogeneity is a problem across the board or not, I'm not sure.
So here's another, this was a key study on which EPA relied. This one's by Schwartz and, Zenobetti and Schwartz.
Okay, so
It's also
now,
mortality.
this
It's
is not
also-
part of our presentation handout, so we're gonna have to focus in on this graph, gentlemen. Okay,
Excuse
so
me.
go ahead, Dr. Goodman.
It's similar. We're looking at the percent increase for 10 parts per billion, increase in 8-hour ozone and mortality, overall and by city. And so there, each row is a city, the vertical line is the zero risk. And, they ordered the cities by, confidence interval amplitude. But, and obviously the smaller the confidence interval, the more precise the estimate. And, but you can see it bounces back and forth from city to city, even with the more precise estimate.
So this is still mortality, right?
This is still mortality, but I guess I was just making the point that
Yeah,
it's difficult in such a short time,
Right.
because we don't wanna be cherry picking anything while we talk about this. We wanna be representative, but we just can't hit every study.
Right. Other clarifying questions from panel? Yes.
Can I follow up?
Yeah, please.
It's not difficult to diagnose mortality, though I've never done it myself, though I suppose I probably could.
maybe.
But one potential problem with mortality outcomes is that if you have a group of subjects and you don't know if they're alive or dead, you can't count them as alive or dead. And so that sort of subject selection losses can contribute to disease misclassification in these kinds of studies. And I don't know if that was a problem or not in any of these, but keep that in mind, that if you don't know if somebody's dead because you don't know where they are, you can't count them.
Okay. Other clarifying questions? I just had one. Dr. Goodman, can you go back to the last slide that's heterogeneity? That one. Okay, so I guess I'm stuck on the x-axis. And what you're saying here, or maybe what others are saying, since this is that we're talking about percent rise in mortality per 10 parts per billion rise in the 8-hour ozone. So obviously this isn't going from 0 to 10 parts per billion. Is this like from 75 parts per billion to 85 parts per billion? How is this x-axis constructed? I guess that's what I'm stuck on.
Well, it varies by city. I mean, or it has to do with what their exposure levels were in each city. So it's, I don't know, I can't remember the range off the top of my head. Do you know offhand?
For Smith, no.
Well, let's say that the average level in the very first city, which looks like it's Denver, let's say it's 75 parts per billion. I don't know what it is. But the point is, how do they get the x-axis?
Oh, I mean, it's the idea is they have the 8-hour measurements every day, and then they look at the death records every day, and they construct a curve and look for correlations.
They construct the curve. How do they construct the curve? Because the curve gives you a slope, which gives you this value. So what's the
Right.
curve?
Do you remember which statistical model they used? I can't remember. Off the top of my head.
Sorry.
Was it just a straight line?
It's a linear regression. And the linear regression, I'm presuming they force it through 0?
I
It's-
think so. I can't remember. They used a hierarchical Bayesian method, but I can't remember.
Okay, so let me get to the biological question. Are they presuming the threshold or not? Because we talked about mode
No,
of
it's-
action
it's
yesterday.
not.
No,
It's not a-
no,
it's
there is
no
no threshold,
threshold.
that's for sure.
Yeah.
I'm just trying to remember if it was linear, but someone's saying it is linear.
Okay,
Yeah, sure.
so they're presuming no threshold, okay. Thank you. Any other clarifying questions? Yes, Mr. Knopf?
Yes, Knos, thanks.
Yes. I'm getting there.
Dr. Goodman, on the second, I think it was your second table with the likely to be causal, suggestive, you have 5 that are in bold where there's a change from 2008 to 2015.
Yes.
You have 5 areas where there's a shift in EPA thinking. You made a comment that it only takes one study to get into suggestive. Tone of voice and body language suggested that you thought maybe that was inappropriate. I'd like you to speak to that as to what in the general, your view and the general scientific community with respect to, you know, how, what it takes in the body of evidence in order to be suggestive. I also wanted to know whether the agency opined as to the reason for why some cities showed statistically significant on that one graph that we've all been looking at, and why other cities did not. Did they have a view? And it'd be interesting to hear it. Thanks.
So I think the word suggestive implies it's more likely than not. And when looking at a body of scientific literature, I mean, the idea is you look at it as a whole and say, as a whole, does it support causation or does it not? And as you know, we'll talk about after the break, the EPA causal determination framework is based on this one put forth by the Institute of Medicine that has 4 categories. It's sufficient, above equipoise, below equipoise, and against an association.
And equipoise is what, please?
Equipoise, so it means more likely than not. So if it's above equipoise, it's more likely than not. If it's below equipoise, it's less likely than not.
So 100 studies, 51 is above equipoise. I mean,
Absolutely not. That's because you gotta think about study quality.
okay, thank you.
But,
All right, thank you.
but the idea is that, and so I don't know why EPA basically stuck in this extra category of suggestive. I think they're calling likely above equipoise. And so I think what should be done is you look at the body of evidence as a whole, and if you're seeing, you know, strong associations, you can rule out confounding chance and bias. You're seeing consistency across studies, coherence across, you know, like epidemiology, toxicology, controlled exposure studies. That's when you get to more likely than not, or likely causal. If you just have one good quality study, you can't, I don't think it's appropriate to just say, well, there's one good study, so there could be something there, so we should say it's suggestive. I think you have to say, okay, there is that study, but then there's all these other studies too. And when you look at that in light of all these others, it doesn't look more likely than not. You shouldn't put it in that category. So that's sort of where I'm coming from. And
And Mr. Knos's second question
was about,
The table, did EPA opine as to why some cities were showing a significant effect and others not? You know,
the last figure,
for the Smith study?
Yeah, the one you're looking for.
this figure right here.
Right, yeah, no, I think they just, I don't think that was really discussed. I think EPA has a lot of, so for a causal association, EPA says chance, bias, and confounding can be ruled out. And for a likely causal, it's chance, bias, and confounding can be ruled out, but, what do they say, other issues remain, or something? I have the language. Chance, bias, and confidence can be ruled out with reasonable confidence, but potential issues remain. But they don't, in both cases, I think even with causal, they don't really prove that you've ruled out chance, bias, and confounding. It's just kind of stated. And then I also think when you say other issues remain, how can you say it's likely? If you don't know about confounding, how do you know if it's more likely than not?
Okay, Dr. Portney?
Yeah, thank you very much. Julie, stay right here on this slide. It's not clear at all to me what the study design was here, or in the Zanabetti study if it's the same thing. So what I need to know is, what are the units of observation? I mean, is this individual data? Because essentially, you have an epidemiological study for every city on there. you've come up with a point estimate of the relationship between premature mortality and ambient ozone concentrations. And so in Denver, where you show that higher exposure to ozone leads to a lower mortality rate, are there 500 people from Denver in this study? Is it census tracts? What are the,
Yes, so they're using, it's air quality data from all of the available air monitors looking at it, and I don't know the numbers offhand. And then it's death certificate data, so you're looking at the whole city. So in each case, it's the whole city.
well, no,
So it's not 500 people or 100 people. You're looking at death certificate data, right, to just count the number of people
okay,
dead.
but then you're presuming that they died in the census tract that that you have air quality data for. And people go to hospitals often, probably more often than not, to die. So the death certificate data is gonna match them to the air quality monitor near the hospital.
No, it's with should be with their residential address, so it's where they live, not the hospital.
Okay,
But-
but then is it controlled for how long they lived at that address? I mean, is there,
Nope.
so they move in with their kids 3 months before they die, and they're matched to that address. Okay, and then,
And they also probably spend most of their day inside, and they also go to work at a different address. So there's,
okay, but that's the way you're able to come up with a point estimate for each of the cities.
right.
Because you have multiple data from each city, right?
Right.
Okay. Just a second comment. You have said, and it's sort of typical when people talk about epidemiological studies to say, well, maybe it's not the ozone, it's something else. And that's true, but then the obligation is to rerun the study, including the something else that you think varies in a predictable way, either positively or negatively with ozone, and put that in the regression. And a lot of times there are criticisms, well, I don't believe this epidemiological study, I think it's something else. Well, then put the something else in there. Because if it really is the something else, then the ozone effect disappears, so.
Yeah, and wait, a lot of people have done that. And so this is a study by Strickland, in 2010, and what they did is, they had their model, and then they did things like in their initial model, they controlled for upper respiratory infections, and then took those out to see if it had any impact, and then they used different kinds of statistical analysis. So I think a lot of people try, but there's, first of all, the data aren't always there. I mean, you have to work with what's ever there. You sometimes just can't do it. And then I think there's other issues with, with collinearity, that's what I was going to say. So a lot of times you have issues with, ozone is correlated with some other pollutant or some other factor. And so if you put them together in the model, they can kind of cancel each other out, so you really can't tell.
Okay, Dr. Goodman, you've drawn up a new slide here.
Oh, yeah.
And you're speaking to this slide?
Well, I don't have to. I was just bringing it up because I remembered in this study by Strickland,
Well, okay, so
They,
can you explain the first versus the second column,
uh,
please?
the first column is a warm season, May through October, and the second column is a cold season, November through April.
And so that means what, please?
Well, ozone concentrations are different in the warm season versus the cold, so that's why they looked at risks separately.
So are we seeing, I can't quite see from my distance, are there differences between the columns or no?
Yes.
There are differences, okay, so what are the differences, please?
It wasn't, the point I was bringing up to answer this question is just, if you look on the first line with the base model where there was
Gotcha.
control for upper respiratory infection, you see you see in the cold season, there is not a statistical association between ozone and
Okay,
pediatric asthma or wheeze, emergency department visits. But when you go to the second line, when you don't control for upper respiratory infections, the association becomes statistically significant. So the idea is it's showing that, like in this study, if you didn't account for these URIs, you might think ozone was associated or causing this health effect, but maybe it was URI, and if that was the case in this study, it could also be the case in other studies as well.
okay, we have Dr. Ryan. Dr. Ryan, you're next.
Yes, I'd just like to go back to this problem you have with the term that EPA has defined for suggestive. And I feel as though you set up a straw man here saying, okay, it says suggestive, that means more than 50%. No, EPA has said that if there is one study that is significant, then that means it's suggestive. That is their definition. That's what they're using. There could be 25 studies that aren't, but one study that is, and that's their definition. I don't have any problem with that, as long as you know what it is.
Okay, the reason I have a problem is because then it gets in the newspaper that EPA says it's suggestive. And if you're not a scientist and you read it suggestive, you're not gonna make that leap that that's how EPA defines
But
it.
we're here to discuss science.
Right, okay.
Right,
But
okay.
that was my only point with that one.
All right, so we're still in the clarifying questions.
Okay, sorry.
Go ahead.
Well, we are here to talk about science, but on behalf of the policy choice community, let me say I find this extremely depressing. And if you were a policy decision maker responsible for deciding, I would ask you, why should I pay any attention to any of these studies?
And that was Dr. Arbuckle. So the response, gentle people? I mean, go ahead, Dr. Utel, you look like you want to jump in.
Well, I don't think you want to look at each study independently. It's a weight of evidence approach ultimately that I think drives whether you feel there's a health effect or not. I certainly agree with you. I think it's very depressing when you have one positive and 25 negatives. I mean, I look at, the effect of coffee on cardiovascular disease or whatever, and the science changes weekly on those kinds of epidemiologic studies. So I think we always ought to have some concern when we see a new study come out. Is it confirmed? Is it confirmed in large numbers? But I don't think, as I said yesterday when we started this discussion, none of the approaches to studying the health effects of ozone, be it clinical, controlled studies, epidemiologic, animal studies, are ideal for the task. And so if you look at each of them independently, unless you're an incredible optimist, you come away with some concern. And so I'm always surprised that the administrator puts so much emphasis on the controlled studies as being the target for making the decision. It really shouldn't be. It should be looking across all of these approaches, and maybe one comes up with a little less pessimism on
Okay,
that.
Dr. Maldonado?
Clarifying point. In epidemiologic studies, even if they are flawed, if there is a very strong signal, you will see it. I mean, there is a limit to how much error that study imperfections can cause. And so that's actually one reason for doing historical cohort mortality studies, for example, in occupational settings, is to see if there's a really large signal there. The other thing is I'm not quite as depressed as you guys are about this. The thing to me is, and what I tell my students is, yeah, there are limitations to studies, and I wish that we had corrected our estimates for these limitations. But part of the art of interpretation of epidemiologic studies is to be able to recognize what problems there are in a study, and hopefully you have enough experience to judge if the extent of the problems are likely to cause a lot of error or not. And so when I interpret a study, I take all this stuff into account. I take all the ifs, ands, and buts into account. And I think you can use what you observe and those uncertainties, even though they're not quantified usually, to help you make a decision.
Okay, go ahead. We'll make sure we answered the question.
So is this a best professional judgment result then? Or do you have a schema for for making that, sort of integrated judgment with all of the possible flaws of the study?
We do have methods for correcting quantitatively for study problems. That's one of my major research interests. Unfortunately, I think you've seen that technique before. It's used in risk assessment a lot. It's called uncertainty analysis, I believe. In epidemiology, we like to have our own terms, so over time it's become called bias analysis. So, but there is a way, and there are several papers that describe quantitative methods for correcting for these study problems based on your knowledge and uncertainty about the magnitude of these different problems, like exposure measurement error. That's what I would like to see done as standard practice. It's not standard practice, so unfortunately, at the moment, it is the former that you said. It's judgment, which is not, I don't think is infallible.
Okay, Mr. Lorenzen?
If I might, can we go back to the slide that has the epidemiological study and shows the curve just of all the cities?
This one?
Okay, that's the one. That's the one. Dr. Maldonado, you talked about trying to correct for uncertainties. Is there a way with a study like this to correct for those uncertainties so that you can draw some conclusion from it? Now, I'm going to state a point that is probably wildly uninformed. As a lawyer and a lay person when it comes to science, I put myself in EPA's shoes or Gina McCarthy's shoes, and I look at that curve, and I see the majority of the cities are showing some sort of a positive correlation. The curve tends to the right side of the zero line. Can conclusions not be drawn from that? And if not, why? The EPA is required to act in the face of uncertainty. How are they supposed to deal with that, given the requirement that they act, even where they're not certain?
So the question was, what would I do, or?
Is there anyone on this panel who believes you could draw some conclusions from this study, despite the uncertainty, despite the possibility of confounding factors? If so, how would you draw those conclusions? What would you do to try and come up with something useful from this? Or, as Dr. Arbuckle just said, Mr. Arbuckle said, do we need to just throw out these epidemiological studies altogether because there's just too many possible confounding factors and they're not useful
I'd
to
like
us?
to hear what he was going to say.
Okay, who is he?
I don't know.
Oh, yes. Dr. Portney.
What he was going to say was, presumably, there's an overall conclusion that was drawn from the entire set of data here. You've displayed this with each of the cities, but for instance, overall, combining all of the cities, did the study conclude that there's a positive and statistically significant association between ambient ozone concentrations and premature mortality?
Their conclusion, our view, is that ozone mortality associations, based on time series epidemiologic analyses of daily data from multiple cities, reveal still unexplained inconsistencies and show sensitivity to modeling choices and data selection that contribute to serious uncertainties when epidemiological results are used to discern the nature and magnitude of possible ozone mortality relationships or applied to risk assessment.
Well, so maybe they're being evasive if you're reading their language, because presumably you could say that the coefficient is points, it's either positive or negative, and it's significant at the 95% level, or it's not.
Almost all of them.
And it's certainly possible for a study to conclude that the evidence shows a positive and statistically significant association between ozone and premature mortality, combining all of the data points together, and yet for certain cities, or you could break it down by age groups or other characteristics, there could be some cities that show a negative effect, even though the totality of the evidence supports a positive and statistically significant association, right?
Well, I think that's a major argument has been made that it's not appropriate to do that, because, I mean, what you're saying is just take a weighted average, and if it's in the direction of increased risk, then we're gonna conclude there's increased risk. But what Smith et al. Are arguing, and others are arguing, is that there's too much heterogeneity that we don't really know what's going on. And if we don't know what's going on, we don't know what a weighted average means. We can't make a conclusion because we don't know based on these data.
So we have a question for Mr. Lorenzen on this idea of can we use this chart or amend this chart to provide more useful information? Any other comments from the panel? Go ahead, gentlemen.
Go ahead.
Julie, when I look at the graph, I see all of the error bars going through zero. I mean, it's not as though these are positive studies that are on the other side of the zero line. I mean, there are a few. So even if you did what Dr. Portney said and you took some kind of average of all of this, just eyeballing it doesn't look like you'd have much of a positive effect from the error bars. I mean, there are 2 or 3 studies that are statistically significant looking at this, but it's not an impressive response across all of these cities.
And we would expect statistically significant findings in 1 out of every 20 studies anyhow, right? Isn't that how we set this up?
So it's said.
Right, right. I
So
think
it
there's
is,
6 out of 90 are statistically significant. But remember, statistical significance isn't the be-all, end-all. I mean, if
Sure.
you see everything trending in the same way, you might not see something. But that brings up the point. These are cities with millions of people, right? So what happens is, it's almost like you have too much power. Is that possible? A lot of studies, you don't see statistical significance because you don't have the statistical power, you don't have the numbers to see it. But in these national studies, even some of the city studies where you're looking at millions of people, you're going to see statistically significant associations. But the risk estimates are so small. So even, that one table I brought up before, this is typical. The risks are all but one, I think, are less than 1.1. Some studies have 1.00 something for risks. So you're getting statistical significance partially because you have such big numbers. But those numbers are, and I would agree totally if someone's about to bring up the argument, even if your risk is small, if you're looking at the whole population, that could end up being a lot of people. The issue is it real? Is it really indicating causation? Because if not, it's not going to impact anyone if you
Okay,
lower ozone.
we're getting into the discussion, which I don't mind doing it, but Dr. Maldonado, do you want to respond?
Just real quickly.
Okay.
Looking at the graph again, I see that the percent rise is actually quite small. So I don't know if you would call that a public health problem or not, a 2% rise or 3% rise in mortality. The other thing, again, I'll probably harp on this for the rest of my life. When I look at this, I ask myself, I wonder what this would have looked like if I had corrected for the substantial exposure measurement error that I know is happening here. And this is not my field, ozone is not my field, so I have not studied how measurement error occurs in these kinds of situations. But if I was an expert, I would have some intuition about the amount of error that 800-pound gorilla could have caused in these studies. And I would not be surprised if it accounted for a lot, if not all, of what we're seeing here.
Okay, we have 2 clarifying questions from the audience. We're going to get to them right now. Sir, you had a clarifying question? Yes. And then the gentleman with the microphone had a clarifying question. So if you could identify yourself and ask your question, that would be great. And then we're going to get on to the discussion.
Tim French with the EMA, and I just had a follow-up to what Dr. Utel was saying. First of all, did all these studies use the same lag time?
Yeah, in this table they did.
Okay.
And remember, this is one study, just
Right.
looking at different cities.
And all use the same statistical modeling techniques?
Yeah, it's the
All right.
exact.
So, but when I look at this, as Dr. Utel was saying, all of the studies, save just a handful, do cross the no effect line. Some do to a great extent. How is it that we go from this, where I would argue there isn't a statistically significant response, and you say that's not the be-all, end-all, but how do we go from this kind of a could be nothing diagram to say that it's, what's the ruling here? That it's likely to be causal for mortality.
Well, I
This
think,
would suggest to me it is not likely to be causal for mortality. I don't understand how we go from black to white.
Okay, so there's the question. Anybody want to?
I also don't understand how we're going from black to white based on this. I agree with you.
yeah, I think what EPA has done is, it's not, in this study, when you take a weighted average, it is statistically significant. And there's many other studies with statistical significance, and they're very small, and EPA's acknowledged you can't rule out other possible issues. But EPA, I obviously don't agree with this, but EPA has concluded that there's enough studies that are showing statistically significant risks, you know, in the direction of adverse effects, that makes it likely.
And one final thing, is the assumption that any 10 ppb increase is the same? If I'm going from 10 to 20, that's the
Yes.
same as going from 70 to 80?
Yes.
Well,
We
why
have-
why does that make sense?
Well, this is the issue that was raised before about the x-axis.
Okay.
I mean, if you're going to presume no threshold, which,
Doesn't matter
based on our discussion yesterday in mode of action, it would suggest that we do have a threshold, because you have to, in order for ozone to get in, you have to get past the detoxifying enzymes. These are a variety of things that people naturally make. So the presumption of threshold seems pretty, well, it seems like you can make that judgment on the basis of mode of action understanding. So redoing the x-axis might help clarify that figure, perhaps. But we have another clarifying question. Go ahead, sir.
Yes, thanks. I'm not sure. I wanted to respond to Tom on most of these circles are on the right-hand side of that vertical line. Doesn't that mean something? Well, the fact is that in science, there are certain rules that we're all supposed to live by. And those error bars are really critical, Tom. And what they mean is that if that error bar goes across the vertical line, you cannot reject the null hypothesis. So you basically, this looks like it's a graded effect, but in fact, if we were to line those studies up, there would be 6 or 7, yes, I see an effect, and the other 83 would be, no, I don't see an effect. The very best study that I could design, I didn't see an effect between ozone and mortality in this city. Those are the data that we actually have. So then the question becomes, and this is the question I have, is that, well, let me preface the question this way. Dr. Maldonado, you were in graduate school 30 years ago, and I was there 50 years ago. But let me point out that in 1984 was the first time Pope in Utah found the correlation between pollution and mortality. That's been 30 years. Every year since then, on average, EPA has invested about $500 million on this issue of pollution and health. 30 years, $500 million a year, that's $15 billion. $15 billion. Is there anyone in this room or in the nation that thinks that if we threw $15 billion at a scientific question of causality, that at the end of the day, we're going to be satisfied with somebody standing up and say, well, it's suggestive? The issue here, Dr. Utel said this, and I agree with him. Ozone has one primary effect on the body, and that's oxidative stress. It's not insidious. It doesn't get into the bloodstream and go to some foreign target in the body. Its action is oxidative stress. We know that. I think that what troubles me is that we are assuming that epidemiology is the only science. And the question I have is, why is EPA so persistent on relying on just epi studies when the question of threshold on the basis of antioxidants is something that could be easily answered for $1 million?
Okay, so, Mr. Pac-Man, your question?
Pac-Ham, I'm not a
Pac-Ham.
game, yeah.
Oh. Oh, yes, right. So I think that was sort of a question comment, and do any of our panel members want to answer the?
I think the question is, I think what we're faced with here is not a scientific question in a sense. We all here see the problem. The issue is, why does EPA, how do we get past this? Because asking about what the controls are here and all that is is off screen for them. They've already, they have the same data that we have, but they're reading it totally different.
Okay, so that sounds like more a policy question. Does anybody on the panel want? Yes.
I'm always willing to, well, my wife said, don't say anything dumb, but I'm always willing to not obey her orders. Just taking an overview, in being around years, and many of us have, I think there's a biased interpretation of data toward the direction that serves the agency's purposes, not necessarily the public's purposes. My wife would say, you shouldn't have said that.
Okay.
Give her my phone number, I'll agree with you.
Okay, Dr.
I'll read
Maldonado,
it.
did you want to add to that? And then we have one last clarifying question at the top.
Yeah, my suggestion was for EPA to spend $1 more billion, and Julie and I will split that, and I think we'll come back in a year and we'll have this clearly solved for you.
Even 60/40 is fine.
60/40? Okay, that's fine. I get the 60.
Yeah. Okay, Dr. Whipple, a clarifying question perhaps?
Yes, Chris Whipple, Enviro. I want to jump back to the suggestive definition as being one high-quality positive study. And it occurs to me that if we have 25 studies and 1 or 2 are positive, we really should think about those studies perhaps as outliers, not as quality studies, and say that's what we would expect to see if in fact there were no effect. And yet
Right.
it seems that's not how the criteria are arranged. Now, I do have one other question about this curve because it is intriguing. And my question is that if you collapsed all the data as suggested, would the much greater numbers of people involved in the study shrink the error bars to the point that you might actually see something or not?
Yeah, it does. So it is statistically significant when you combine them all. The question is whether it's appropriate to do that because of all the issues we've talked about. What?
Okay, we have another clarifying question? They're shrunk already.
Yes.
Oh, from
The-
right, from the Bayesian.
Yeah.
Yeah, these are actually already shrunk because of the way that he did the statistics. But then, again, so the confidence intervals are actually shrunk for each city because of the way the statistics were done. But then if you were to combine them, the cities together in one estimate, they'd be shrunk even more, and the average would be statistically significant.
Okay, so I just want to go back to Dr. Whipple's point to make sure I understand it. You're saying that if we look at all these studies, that let's say there's 20 studies there, I think there's more. For every 20 studies, we're going to expect to see one statistically significantly positive finding just due to chance alone, because that's how we design the statistical significance statement. Okay, so if you said there's 90 studies here,
90 cities, yep.
there's 90 cities, so we're going to expect 4.5, roughly, positive findings. And how many do we have?
6.
6. Okay.
Is it only 6? I thought I counted 10. Were they just too
Oh,
close?
I thought it was 6, but I haven't counted in a while.
Okay.
Which graph you use.
And that's true too, it depends on which graph.
Okay,
I just
why don't
put
we
one
segue to discussion, and we're gonna,
for 10 minutes.
we're gonna discuss, we're gonna go to 10:15 here, so I have a little bit of time. that we squirreled away for lunch. We're gonna use it.
6 or 7. There's one that's really
And we're gonna
close.
break at 10:15. So the two questions before us are, and not surprisingly, we've kind of talked about them already. What associations are causal? And what criteria are used to make this decision? So the causal associations are these various studies, and they're assigning causality to ozone in particular. So any thoughts on this, panel? Yes, Dr. Phelan.
When I was a physics student, graduate student, and we were looking at models, what I was told was that essentially every event in the universe is causal for every response. The question is, what is the strength of the association? You know, I do this, and the moon responds, not very much. So, to me, the very concept of causality is meaningless unless you talk about the strength of the association. You know, if a major asteroid goes by the moon and pulls it out of its orbit 1 or 2%, that's significant. But when I do this, if 10 to the minus 30th millimeters is the deflection of the moon, that's not significant. So to me, the strength of the association is far more important than whether something's causal or not. I don't know if that's clear, but
So in this particular case, you look at these data, do you have a sense of the strength of the association?
it's tiny. And so although you could show possibly, you could argue for causality, when I see a strength like this, it's a moot question because the effect is so small. Now, the answer to that is, well, 1 person in 5 million died that day that otherwise wouldn't have. And if you're that one person, you know, it really makes a big difference. But as a scientist, I think that's not the way to look at it. I think that's illegitimate. I think that the strength of the association is, and I think Bradford Hill would say first, the first thing you consider when you're thinking of causality.
All right, Dr. Maldonado?
We've been wrestling with this question of what's causal for about 250 or 300 years now, and I don't think we've come to a perfect way of making that assessment. The problem is that we can't directly observe a causal effect for philosophical reasons. And so what associations are causal? I don't think we have the tools at the time to make that determination most of the time, except for in special situations where which don't apply here, where I can actually see it happening, like a shotgun blast to the head. I can say that that's causal because I can see it happening, and I can examine the after effects and I can understand the physics of it. But that's not where we are here. For situations like this, I think we're never going to know if it is indeed causal or not. It's your opinion, it's my opinion. And one of the problems is that our observed data are not corrected for all the problems that occur in a study, which makes it hard for me to determine if something is causal or not. Bradford Hill criteria, those kinds of criteria we know they're not infallible. And a lot of epidemiologists don't even use them and try a different approach, try to estimate what a causal effect parameter by correcting for all these things that go wrong in a study. Still, we don't know how to do that perfectly. Some people use statistical significance. Well, the problem of statistical significance here is that these are observational studies, and so the calculations of statistical significance make all kinds of assumptions that don't even apply here. Basically, those calculations assume that there's no error in the studies, which we know there are. And it also assumes that we understand the process that we're studying to the point where we can write down a mathematical equation for the probability distribution for random error, which we can't here because it's not a randomized trial. I can do that in a randomized trial. And so most of the tests that we use assume that we have a perfect randomized trial. And so statistical significance is, I don't, personally, I don't even know what to do with these error bars because I know they're fantasy numbers based on these assumptions that don't apply in these situations.
Okay, thank you. Dr. Ryan?
Yes, I'd just like to go back to Dr. Phelan's comment about significance in these data. And Dr. Goodman, correct me if I'm wrong, but if you do this, you said it was statistically significant if you looked at all of these. And if I were to look at all of these, I might estimate something like 0.5%.
Yeah, I think.
Yeah,
I think that's
I'm
right.
just,
Yeah.
drawing some lines, trying to do some
Yeah.
ocular statistics, as I refer to it. If we're talking about in these 90 cities, a population of, I don't know, 100 million, something like that, 0.5% is still a pretty substantial increase in total all-cause mortality that's associated with this. So I think that's a significant effect, and we really should keep that in mind. We're talking about a lot of people here. And small effects, yes, 1.004 or whatever it is for the risk estimate on one of these things here, which I think was the smallest one I saw in there, still represents, 10,000, 100,000 people, somewhere in that range. And I would find that significant.
Okay, any other comments from panel members? Any clarifying questions from presenters? Okay, any clarifying questions? We have 2 questions from the audience. You want to take your turn? That's fine. Then I have one from the web. Go ahead.
I just have a comment that going back to the causation, EPA's suggestive causal, I mean, to me, the takeaway from that slide is the fact that the evidence is getting stronger that it's likely a causal relationship, not nitpicking these individual studies, looking at whether the statistics are 0.5% or 2% or whatnot. I mean, the overall evidence is increasing, and the likely to be causal category actually states that chance and bias can be ruled out with reasonable confidence. So to me, that's the big takeaway from that slide. Not that the idea of this issue of statistical significance. I mean, I agree that 0.5 is important when you're talking about the number of people that we're discussing here. So that's just my comment.
Okay. Do we have any panel members who want to respond to that comment before we get to the next one? Okay, if you would identify yourself. That was Elena Kraft, the EDF. And sir, what year?
Andrew Hoeksema, Capital Area Council of Governments. So my question is related to uncertainty and how to interpret, if you could bring up that graph again.
This is the last, okay.
That
one?
Yeah, that one.
Okay, good.
So, we spent quite a bit of time yesterday talking about the language in the Clean Air Act and discussion of how to set standards and that they've got to be set, no more, no less than necessary to protect human health with an adequate margin of safety. So my question relates to how uncertainty in a study or a set of studies like this plays into that adequate margin of safety, and how you as scientists would sort of look at this from that perspective. The other, and specifically what I'm thinking about is, sort of as a given, most scientific studies look at a 95% confidence interval. There's nothing magic about a 95% confidence interval. If you want a higher level of confidence, you have larger error bars. If you are satisfied with a 90% confidence interval, you get smaller error bars. So how, if you looked at this from one of, if you said, well, let's have it be 99% or let's have it be 90%, you might come up with different conclusions about how to interpret this data. So what are your perspectives on sort of confidence levels and how to interpret those in relation to the NAC setting process and these kind of data?
Okay. So gentlemen from the panel, any thoughts on how to deal with this question?
I haven't really thought much about the what did you call it, the
Margin of safety.
margin of safety
Mhm.
in terms of confidence intervals. So I'll have to defer that to the $1 billion grant.
Okay.
Have you?
I actually think that's a separate issue. Like, what we're dealing now is causality. Does ozone cause these effects? And then if the answer is yes, then you figure out at what exposure level and what's the margin of safety you need. And I guess that margin of safety is a policy question, not a science question.
And if the answer is maybe, is it still more policy or more science?
Well, well, what it is, and that's an interesting point, what EPA does is takes causal and likely causal associations and then does the risk assessment based on those endpoints. So what happens is whether it's causal or likely causal, that's almost, it basically disappears once you get to the risk assessment. It's like we're just starting from zero. And actually that's where maybe, the confidence interval should come in, because there should be some way of accounting for that uncertainty, whether it's causal or likely causal. When the risk assessment comes, there is some uncertainty accounted for, and Sonia's gonna talk about that at the lunch talk, but certainly not all. There's a lot more uncertainty that isn't accounted for.
Okay. I just have one thought to add, but Dr. Phelan, you go ahead.
Okay. I was disturbed as a kid by the Alice in Wonderland story. And I understand it better when I start looking at what's happening here. One of the assumption about the question about margin of safety, is it the margin of safety related to a dose response curve for FEV1? Or is it a margin of safety for the people of Texas or the people of the United States for about your decision? And human health involves a lot of factors, including things like, does the breadwinner have a job? So I have a feeling of unreality when we're talking about what's the safety for human health based on those data, because we're ignoring the big factors that affect human health. I also have the Alice in Wonderland emotional response when people say an increment is what we're talking about. That implies that going from 0 to 10 ppb has the same implications for health as going from 200 to 210 ppb. And that's just so unrealistic. So now I understand why, as an 8-year-old, that story bothered me so much, is that there's some reality to it, and I didn't realize that I'd be in that world as an adult.
Right, so this concept of margin of safety has got various aspects to it. From a technical risk assessment perspective, it really goes to what we said yesterday. It folds in, or encompasses, a better word perhaps, this idea of error bars or sensitivity analysis and sensitive subgroups. And there are publications and logic behind different quantifications of margin of safety. But in this particular case, it goes to sensitive subgroup, because that's what the act is based on, which is not inconsistent with what risk assessment people do worldwide. They go for sensitive subgroup. And you can talk in terms of, do you have enough margin of safety to protect sensitive subgroups? The information that Dr. Lang showed yesterday, where we have FEV1s, and we've actually got quantifications for what are considered to be sensitive subgroups, is helpful maybe in understanding what the margin of safety might be for that particular effect for ozone.
Correct. Yeah, and as a child, my dad worked on the railroad and he was a taxi driver and things like that. And the margin of safety for our family was whether or not he was bringing in money for food.
That's a different aspect from what I was.
That's right, and that's the Alice in Wonderland thing. And I know one statistician and physician was appalled that he says we're looking at the ripples on a pond and not the pond.
Right.
And it worries me to see so many grown men and women spending their time on some of these things.
Right, that last figure, can we call up that last figure one more time? Because I want to get to a point, Dr. Phelan, you said, and then we're going to go to 2 more points.
I'm sorry, I thought we were going to take a break at 10.
Okay, we're not gonna take a break at 10.
10:15.
10:15, sorry. So, well, anyhow, we can, what that curve is, that on the x-axis again, the x-axis of that curve is making a presumption of linearity or no threshold. And so I suspect, that you're absolutely right, there is a difference between 0 to 10, because we looked at filtered air, and that actually improves FEV1s.
Yeah.
Maybe
Yeah.
because of these protective
There's
enzymes building up.
There's a biphasic response for many
And
chemicals.
200 and 210, and somehow, I think if you worked that relationship into these, in other words, if you didn't do linear regressions, and you made your x-axis different, you might get a different relationship there. And so therefore, it might be protective in Denver because of something Dr. McClellan said yesterday, hey, the dose makes the poison, right? So if the average concentrations in Denver are 40 and the other cities are 80, well, of course you're gonna see a difference, or maybe 120 or whatever.
Mike,
So-
we've looked at, we've looked at the design values for these particular cities and compared them to their, the risk estimates, and there's no correlation between at least the design values. The design values are that's the fourth highest ozone concentration over 3 years. So it's the form of it's the form of the standard. There's no correlation between those estimates and their design values. So you see Los Angeles there is sitting around 0, and it's got very high ozone concentrations. And at the very bottom, I think is Colorado Springs, has quite a high risk estimate, and it's maybe 30 parts per billion lower ozone concentration. And it's 70 miles away from Denver, which is at the very top of the graph, which shows a negative association. So at least in terms of total ozone concentrations, we don't see that correlation.
I guess I'd like to see the x-axis different on the basis of mode of action.
I don't
We do
agree
have
with that.
something from the web and Dr. Porter. So Dr. Porter, you could go first, and then the web, and then we're gonna go into our next question.
Yeah, just very briefly for the record, epidemiological studies don't have to and often don't use linear probability models. And so I think it's important not to assume that every study assumes that the difference between 100 and 110 is the same as the difference between 0 and 10.
Good point.
Epidemiological studies are done using Poisson distributions, survival functions, and all kinds of things that make it possible to estimate different relationships at different parts on the exposure axis. So people
Right.
shouldn't think that every one of these studies is done using a linear probability model.
Yeah, and Dr. Porter, do the epidemiology studies also, I'm sorry. Yeah, do they also use this idea of models that incorporate thresholds or understand mode of action? Is that something that they routinely do, or?
Well, I'm not close enough to it now to know routinely, but you certainly can do that, and Julie's in a better position than I am to answer that question.
Yeah,
All right, thank
very,
you,
very few of
Dr. Portney.
very few of the ozone studies incorporate thresholds, and a lot of them say, basically say there's no evidence for a threshold, where the argument's been made is that, I mean, they're saying there's no statistical evidence that a threshold model better explains the data than a non-threshold model. But, you know, we would argue that if you know biologically there's a threshold there, the fact that statistically there's no difference doesn't mean the non-threshold model is correct. And then another issue has to do with, we've written a paper, Lawrence Romberg's the first author, that because of exposure measurement error, you can actually mask the threshold at lower concentrations. So it's there, but you're not going to be able to see it because of that issue.
Okay, we're gonna go on to our next discussion question. I think we've talked about number 6 a little bit.
Was there a web question?
Yeah, there was a web question, so let's do that before we get to question 7. This is from Thomas Didek from the webcast. It's for Dr. Goodman. In the Smith et al. Study, many of the data from different cities have confidence intervals that include 0. Shouldn't we be just looking at those cities for which there is statistical significance?
I'm really glad that question was asked, because I think that it's a common misconception, the idea that you can basically, any null associations you could just throw out, you just ignore. If any study or any part of a study shows statistical significance, that's evidence there's something happening. But the idea is you cannot look at just positive findings in isolation. You have to look at all the findings together. And if you look at a whole bunch of studies asking the same question in the same way, with George's caveats, you should be seeing consistent results. And if you're not seeing consistent results, the proper way, or the most appropriate way to interpret this, I think, is to say that the evidence isn't sufficient to say that ozone is causal. You're just seeing chance fluctuations due to chance, bias, confounding, or some other issue. It's less likely, it's certainly possible, but it's less likely that the few cities or the few studies or the few actual analyses showing statistical significance those are the only ones right, and then the other ones you just ignore. And I feel that happens a lot. And so people are misinterpreting the data because they're, instead of focusing on, okay, what are the methods, what are the analyses we should look at, and let's look at them all together, they're starting with the results and saying, here are the positive results, and I'm going to just focus on those and ignore everything else.
Okay, Dr. Maldonado, do you want to add to that?
Nope.
Or subtract?
Nope.
I think you said no.
No.
No, I'm sorry, I think your response to the question was
Oh.
no, we shouldn't just be
Yes.
looking at the cities
No,
for which,
sorry.
okay.
That was a long answer.
Okay. We're gonna go on to the next question. We're gonna take a break at 10:15 regardless whether we get through it. Next question is, considering exposure measurement error, how do ambient air concentrations in epidemiology studies relate to personal exposures and impact the interpretation of results of these studies? So we're measuring ambient concentrations, and we know that some of the personal exposures inside the house are less. I heard someone say 30% or maybe 70% less. They're only 30% of what's out in ambient, but
That's high.
I would just hearsay. I'm not sure that number's right. So any thoughts on this, gentlemen from the panel? Yes, Dr. Ryan?
Actually, yeah, the 30% I think is towards the high end. It's more like between 10 and 30% value for ozone in an indoor environment compared to the outdoor environment.
Okay.
There's a number of different issues that are going on here that I'd like to address. And the first of these is what ozone really is. I mean, we saw yesterday and have seen a number of times since that the ozone chemistry is very complicated. Essentially, ozone is not produced, it's not released by anything. It's produced in the environment by secondary reactions, interaction primarily with sunlight, hydrocarbons, oxides of nitrogen, and so on. And it produces, a milieu, if you will, a soup, as it's often referred to, of compounds that are really just indicated by ozone in the environment. So ozone is more or less an indicator pollutant. Dr. McClellan yesterday, given the history of the ozone standard, and I'm putting ozone in quotes right now, you can see the little air quotes around them. In 1977, I noted that the standard was really on photochemical oxidants, and it was changed to ozone later on. Really what we're interested in is the photochemical oxidants themselves and their impact, because once it gets inside the body, we start to see interactions with various systems. We talked about the toxicology yesterday. Ozone is just one of these things that can react that way. Other materials that are produced include essentially oxidation products of hydrocarbons, peracetyl nitrates, peracetyl compounds in general, peroxide radicals, ultimately producing hydroxyl radicals in the environment that then interact with all kinds of organic materials and kind of clean it up, oxidize it along the way. And these are the things that are really likely influencing health. Ozone is just one of many, but ozone is indeed an indicator. Ozone concentrations in the environment are really kind of controlled by photochemical equilibrium. As long as there's still sunlight coming down, all of these reactions occur, and that's why we see this diurnal pattern of ozone being higher during the day and less at night, with certain exceptions, one of which is a study that I mentioned yesterday regarding the Great Smoky Mountains National Park. Ozone is essentially removed by oxides of nitrogen, in particular nitric oxide, NO, during the nighttime. If there's no driving force of the energy being put into the system, ozone sits there, finds a molecule of nitric oxide, reacts with it, oxidizes the NO to NO2, releasing oxygen, and essentially ozone is gone at that point. So what we're measuring, even in central site monitoring, is a surrogate or indicator for the type of things that are likely to produce health effects, these being the photochemical oxidants themselves. So now let's go inside. Inside, I said the typical numbers are 10% to 30% ozone concentration, essentially dependent on, the a little bit dependent on the outdoor concentration. The ratio is somewhat dependent on the outdoor concentration, but it's more dependent on how many windows you have open and so on. What is the difference between the indoor environment and the outdoor environment that causes this? Well, first off, the sun doesn't shine inside. So if the sun doesn't shine inside, essentially we don't have any driving force to produce that ozone anymore. So we don't produce the ozone, it just kind of sits there. Well, ozone is an incredibly reactive molecule. It reacts with pretty much anything. It can react in two different ways in the indoor environment. The first of these is by gas phase reactions, homogeneous gas phase reactions. Similar to what goes on outside, but we don't have the driving force that drives back to make more ozone. So essentially we see a loss of ozone over time due to these gas phase reactions. The second of these is heterogeneous surface reactions. Essentially, the chief difference between the indoor environment and the outdoor environment is that the indoor environment has no sunlight, and secondly, it has a lot more surface to area, surface to volume ratio. We look in here, we've got surfaces like the floor, the walls, the ceilings, and so on that are not mimicked outside. So many reactions occur on the surfaces themselves. The surface more or less acts as a catalyst. Material comes down, sticks to the wall, let's say, ozone comes along, interacts with whatever molecule is there, and produces something new. What we see in the indoor environment is a loss of ozone, but the ozone doesn't disappear. The energy associated with the ozone does not disappear. It is merely transformed into another form. For instance, if there is a source of oxides of nitrogen in the indoor environment, a combustion source, one could very well produce other oxidizing materials. One of the most commonly produced is nitrous acid, HONO, which is itself an irritant. It's not as much of an irritant as a number of other things. HONO is very soluble. It can also be oxidized to nitric acid, a more potent acid, as it were. Nitrous acid is a weak acid in the chemical sense. Nitric acid is a strong acid in the chemical sense. So the fact that we see this massive drop-off, a factor of 10, a factor of 3 to 10, is not completely mimicked by the effects. The effects also include the other materials that are produced. We did some work about 15 years ago, and several papers, we published three papers in particular on this, that showed for every mole or molecule or whatever you want to call it, of ozone that comes into the indoor environment, we would produce something on the order of 0.3 of a mole or 0.3 of a molecule of formaldehyde or other aldehyde materials through secondary reactions. My colleague Charles Weschler from Battelle, working on the other side, that's essentially ozonolysis occurs when you oxidize double bonds. I won't get into any more detail than that. It pulls essentially breaks the molecule in half. He found that the other half of the molecule was responsible for the production of particulate matter in the indoor environment. In particular, reactions with pinene and limonene. Pinene is the pine smell that you have in pine sol. Limonene is that lemony smell from lemon pledge and so on. Things that are used typically in the indoor environment. Interactions with ozone with those materials actually produce particulate matter in the air. So yes, we see a reduction, and that causes the misclassification biases that you might say, looking at well, it's not the misclassification bias, exposure measurement error associated with using a central site monitor, but it's not as bad as it might be because some of these other things that are produced that also may have some of the same effects. So yes, there is exposure measurement error. As a matter of fact, my colleague Jeremy Sarnat has done a good deal of work in that area, publishing a paper in the mid-2000s discussing this whole issue. And he has done extensive work on panel studies associated with ozone and so on. But we need to understand that other things are occurring at the same time, and there may be effects associated with them.
Okay. Thank you, Dr. Ryan. Any clarifying questions from panel members on Dr. Ryan's thoughts? Clarifying questions from presenters?
I mean, I agree that there's probably other things that are formed from the ozone, but ultimately the standard is based on ozone and the health effects that are associated with ozone and not with formaldehyde or other aldehydes or, so I think that is what makes it so difficult. Because if the standard is based also, as we talked about yesterday, on the controlled exposure studies, which are clearly just, this exposure to ozone as having the effect on the, FEV1 decrements, then, it's not these other things that are causing it. It's,
And Dr. Sonia, the question is, Dr. Sachs?
And so the question is, is it appropriate then to, even if there are these other effects, is it appropriate to base, a standard on ozone, or do we need to be looking at, what are the other contaminants that are being formed that maybe they are more toxic, and maybe those are the things that we need to be regulating and focusing on.
As I suggested, ozone is really a sentinel or a marker for all of these other things.
Mhm.
Now, in chemistry, we tend to flow downhill.
Right.
So ozone is a fairly substantial oxidant. Some of these other things I mentioned are less substantial. That's why the
Yeah.
reaction is going in that direction, particularly in indoor environment.
Yeah.
I sort of object to studies, and Mark, I apologize for you for this thing immediately, that only put ozone in there, because there are a number of other things that can go on. I like the standard that was present in 1977, where they were looking at photochemical oxidants. The problem is we don't have a meter that we can stick up in the air and say, this is the photochemical oxidant meter. So we would have to be measuring a whole bunch of other things. It's still a sentinel in the environment, and I defer to my colleague, who is much more learned in this matter, whether he thinks that an ozone chamber study is sufficient to understand that.
Right.
So, I assume you're deferring to me, but let me.
You are my more learned colleague,
Yeah,
after all,
right. Within the chamber, Barry, there are all kinds of surfaces.
What typically are the because the chambers I work with are polished stainless steel, so there isn't really.
Ours is not. It
Okay.
never has been. And there is all kinds of equipment within the chamber itself. So we've always considered that as being a mechanism for the oxidation products that you're going to see with ozone, recognizing, in fact, we're generating, pure ozone, but there are other materials coming into the chamber as well. We open the doors, there are lots of potential. I mean, you make an interesting point, and certainly the limonene and pinene issues are gaining attention and interest, whether they cause airway changes and airway responses. I really don't think we know the answer to that. I guess my question is, if we had a stainless steel room and no other surfaces within the room, what would happen to the ozone? Would it break down into these kinds of products, or is it really the surfaces that are there and the other materials in the room that are responsible for it?
In a typical indoor environment, we've had people living there for quite some time. There's been cooking going on. There's off-gassing of materials and so on. So there's a bunch of stuff stuck on the wall. And if you don't believe that, wash your wall sometime, and you'll be able to see that. In a stainless steel chamber, if it's polished correctly, there shouldn't be any reactive surfaces in there. That's why they're designed that way. Now, your chamber may be more indicative of what's typically found in an indoor environment. There might be a chair for the person to sit in. There might be a rug on the floor. There might be a table so that, when you leave them in there for 4 hours, they don't go crazy. They can actually write something or read a book or whatever. So there are likely to be more sources in there, but they're not likely to be the same as they are in the typical indoor environment where day-to-day activities go on.
Well, there's no cooking, that's for sure, but there's a spirometer.
Well, you leave them in there long enough, they might want something,
Okay, I think at this point, we need a break. But we have 2 questions. If it's quick,
I'll be
Dr.
quick.
Lang, please.
I'll try and be quick. So I was wondering if, because ozone is reacting with indoor surfaces, and really everybody's indoor surfaces are going to be a bit different if they're spraying Pine Sol and Pledge all over the place, does this make the exposure measurement error worse? Because now not only do we not really know what that particular person was exposed to in terms of ozone, but their indoor environment and how it's reacting with ozone is going to be different even from their neighbors. Does this make it even more complicated to interpret?
Well, it makes it more complicated. I don't think it makes it any worse. simply because we're using only ozone, and we're saying that the ozone is markedly depleted. And because it's markedly depleted and we're taking the central site monitor, there's misclassification or a bias or exposure measurement error, or whatever you want to call it, associated with that. My point is, I don't think it's as bad as it might be, because there are these other things. Now, there's going to be a good deal of variability associated with that. And you know, there's a mix of these things that maybe 80% is effective as ozone, or 30% is effective as ozone, or 50% of effective as ozone at impacting upon the lung epithelium and getting through these, you know, hitting these things. I don't know about that because people haven't done those experiments. But it's likely to be better than just the, you know, the drop-off that you see and say, these people aren't exposed in the indoor environment, excuse me.
Okay.